So in this lecture, we're going to talk about classical scattering of light and electrons. So consider some high energy light hitting some stationary electrons. So what is the classical expectation we have about this scattering process? Now, since, according to classical theory of electromagnetism, light is a wave, we would expect that the electron exposed to the electric field of the incident light would start oscillating in the frequency of the incident wave. So let's draw some pictures. So we have, say, some electrons sitting stationary, and then we have some electromagnetic wave with a certain frequency that's passing through. So that is going to be the direction of propagation. So when this electromagnetic wave is passing through, what will happen to the electron is that it'll experience the electric field of this wave. So it'll start oscillating up and down. So these are the directions of oscillation, right? So we know that whenever a charge accelerates, it emits its own radiation. And the frequency of that radiation would be given by the frequency of oscillation. So as this electron, oscillates up and down, in the frequency of the incident wave, it will emit its own radiation, right? So it will emit its own radiation. But we expect the frequency of this radiation to be the same as the frequency of this oscillation. So we will expect that the frequency of the scattered beam will be the same as the frequency of the incident beam. But we know that electromagnetic waves also carry momentum. So it'll also impart some momentum to this electron. So because of that, what will happen is that although initially the electron was at rest, it'll start accelerating in that direction. So this would be the direction of acceleration. So as a result, the electron will also accelerate, and because when it's accelerating in its reference frame, in the rest frame of the electron, what it'll see is that the frequency of the incident wave will decrease due to the Doppler shift. And because of the Doppler shift, because the red shifting of the incident wave, the frequency of oscillation of the electron will also decrease, and therefore the radiation that the electron was emitting, that frequency will also decrease. So as time goes on, the frequency of the radiated or scattered wave will go down. So as a result, so when will this stop? This will stop when the whole wave train has passed the electron. So what we expect to see from classical physics is that whenever an electron is exposed to some high energy frequency of light, that it's going to emit light whose frequency is going to change continuously. So its frequency will start with the same frequency as the incident wave, and then it'll go down, and the lowest frequency that we can expect to see will be determined by how long this wave train, the incident wave train, is. So now the question is that what we see? What turns out is that that's in experiments that is not what one sees. Instead, in experiments, what happens is that if you have an electron that is sitting still and then you shine some very ultraviolet radiation towards it, then what happens is that the electron kind of recoils in some random direction, and the electron scatters the beam. I'll use a different color. The electron scatters the electromagnetic radiation, and depending on the angle of scattering, the wavelength or the frequency of the scattered wave depends on this angle. So this is more reminiscent of a scattering of two particles rather than a continuous process, which is what we have described over here. So, this is the way that people observed at the beginning of the 20th century how classical electromagnetic theory failed to describe the scattering of electrons and ultraviolet radiation.